Hello, and welcome back to Data Literacy and Data Visualization. I'm Professor Braumoller, and I have a confession to make. When I talked about theories and hypotheses in the previous lecture, I sort of glossed over a fairly important topic, and I want to take the next few lectures to talk about that topic in considerably more depth. The topic is called identification. Now, what do I mean by identification? Well, simply put, when we look for correlations, especially in observational data, we all know in the back of our minds that when you find a correlation, it doesn't automatically translate into a causal relationship. It isn't automatically evidence of a causal relationship. We tend to ignore that when we're handing in papers for seminars or looking for a relationship of interest, to support an argument we want to make on Facebook or something like that. But, we all know deep down that you can't automatically infer causation from correlation. That said, one of the fingerprints of a causal relationship is generally a correlation. So, how do you know, how can you be, when you're looking at a correlation, how can you have some reasonable assurance that it's the result of a causal relationship or of the causal relationship that it purports to be? So let me run through how this is going to work in principle. Let's say you have an argument that some variable x causes some other variable y. Now, your variable x is not going to be the only thing that causes y, whatever y is. There's going to be other stuff that causes y as well. So if we came up with a very, very abstract representation of the relationship that you're looking at, it would look something like this equation down at the bottom here: y is equal to a function of x plus e. Now, people get a little bit weirded out, I think, sometimes when I write y is a function of x, because it doesn't refer to any concrete function of x. It's not like y equals x squared or something like that. It just means that y is somehow related to x, and we don't really care how for the purpose of this illustration. So when you're making this claim, you're making a few specific arguments. One is that x causes y, as you can see with the happy little green arrow here. Another is that some of this other stuff also causes y, right? Whatever other stuff you're not examining, that causes y as well. You're also claiming that this other stuff that you're looking at, these omitted variables, don't cause your causal variable, right? That is, your causal variable isn't just epiphenomenal, right? In this model, potentially, if E causes X, then potentially what could be going on is that really E could be causing Y via X, and X could be relatively unimportant. So if E causes X, that creates potential problem for the causal relationship, or the causal argument that you're making. Another potential problem is reverse causation. If you find a correlation between X and Y, it could be that Y is actually causing X. And finally, a confounding relationship could occur where you've got some other variable that you haven't examined that's causing both X and Y. Okay, so the real problem that comes out of all of these diagrams and arrows and everything else is that it's very difficult to assess most of these relationships. It's very difficult to tell whether or not you've got a confounding variable that's causing both x and y, or whether you've got, your omitted variable e causing x. And if any of them are wrong, then that simple correlation that you're looking at between x and y really doesn't reflect a causal relationship between x and y. And that's a problem, because what you want to get at is the causal relationship between x and y. Now, a great example of this is a debate that takes place over the effects of gun ownership in the United States. And a lot of people argue that number of gun deaths is a function of the number of people who own guns, or the number of guns that are owned, and some other stuff. right? So the relationship of interest here is whether or not gun ownership and gun deaths are positively or negatively correlated. But even if you show a positive relationship between the number of gun deaths and gun ownership over time, you still have a lot of questions to answer. Could it be that a rise in gun deaths increases gun ownership? That is, the more people get shot, the more people feel like, well, I really better go out and get a gun and protect myself. Could it be that there's a confounder, right? That the big salient shootings that we see in the news inspire more shootings and inspire people to buy guns to protect themselves, right? That would be a fairly clear causal story that doesn't involve gun purchases increasing the quantity of gun deaths. And finally, is gun ownership just epiphenomenal, right? Is it just the most convenient way to kill people, but if people were deprived of guns, they'd use knives or some other means to off their victims rather than shooting them? Now, these aren't necessarily, that last one in particular, I think, is not an especially plausible argument, but there are arguments that you have to take into account if you're going to claim that your correlation between gun ownership and gun deaths is plausibly causal in nature. So how do you go about making that argument that you've got a plausible causal relationship? Well, that is the realm of identification. Identification is the process of eliminating the influences of all those other variables so that we can be as certain as we can. It's not always going to be perfectly certain, but we're going to be as certain as we can that a correlation between X and Y really represents a causal relationship between X and Y. Now, I'm not going to claim this is easy, but I am going to claim that it's worth trying to do when it's possible, and it's worth thinking very hard about how to do it. So how do we do it? How do we get identification? There are, in general, two ways. The first way is to use research design to get identification. That is, you look for situations that naturally occur, sort of natural experiments, for example, in which you can be fairly certain that you've got identification. Okay. Another way to do it is using statistics. That is, once you learn more about statistics, you'll find that there are a handful of techniques like matching two-stage least squares, recursive bivariate probit, techniques, a fairly wide range of them, that allow you to get identification from your data, even if the data don't meet the standard of sort of a natural experiment. Okay. Now, in this class, we're not doing statistics per se. We're a little bit in a couple of lectures down the line, but really, for the most part, we're not doing math. We're not doing statistics. So we're not going to be anywhere near the point where we could do model-based identification using statistics. What we can do, however, is understand research designs that will better allow us to get at identification, better allow us to get at a causal relationship between X and Y. So the next few lectures are going to be about variations on design-based identification. And we'll talk about natural experiments, we'll talk about what's called a regression discontinuity design, and we'll talk about difference and difference estimators. In each case, I mean, these sound kind of obscure, but really the intuition is very straightforward. I'll convey the intuition about each one, and then once I've done that, I'll give you a couple examples to show you how they work in practice.